This is worksheet 2 of the chemical calculations packet, and in this worksheet we are going to learn how to calculate a simplest formula, which is also sometimes called an empirical formula. So the idea behind the work that we're going to do is that a formula like H2O or NaCl, any formula like that, is really a ratio. It's telling you how many atoms of one element you have for how many atoms of the other element. And these are actually mole ratios, so they're in not molecules or atoms or liters, but in amounts of moles. So if you think of the formula H2O that most of us are familiar with, right? What that's really saying is that for every 2 hydrogen atoms, there is 1 oxygen atom. Now, that's the simplest or most reduced way of explaining the combination of hydrogen versus oxygen. If you look at a water bottle that contains water, that doesn't mean that there are exactly 2 hydrogens and 1 oxygen, right? There are way more atoms than that. But it means that if you totally reduce it down, for every 2 hydrogens, there's 1 oxygen. Or another way of saying that, there are twice as many hydrogens as oxygens, right? So if somebody told you there are 1,000,000 oxygen atoms in this sample, you would know that there must be then twice as many, or 2,000,000 hydrogen atoms. So it's a ratio. All right, so in this worksheet, we are going to imagine that we are scientists in a laboratory and we have been given a sample that has been analyzed. So if you look at this example problem, you are given the information here, the analysis, that the sample you're looking at contains 36.11% calcium and 63.88% chlorine. So it's all calcium or chlorine because those two percentages add up to 100, right? And so we want to know, all right, what would be the formula that would describe this compound? The simplest formula, the most reduced formula. So the first thing you want to do just to make your life easier, since percentages are numbers out of 100, is let's just assume that we have a 100-gram sample. All right, the math works out. You can assume you have any amount sample that you want because we're talking about percentages of a whole. And if you do that, that means that these percentages convert directly into grams, right? It's because of the definition of a percent being a number out of 100. So you now know how many grams you have of calcium and how many grams you have of chlorine. Now, remember we said that formulas are not gram or atom or molecule ratios, but mole ratios. So what we need to do is we need to convert the number of grams that we have for calcium and chlorine into the number of moles. And you should remember how to do that because we've been doing it since the mole packet. We use the molar mass, right? So if you go look up calcium on the periodic table, you'll see that it has a mass of 40.08. And if you look up chlorine on the periodic table, you'll see that it has a mass of 35.45. Now, some of you might think, oh, but chlorine, that's one of those Hofbrinkel molecules. There's always 2 of them, right? Remember, that's only when chlorine is all alone. In this case, we're talking about chlorine that's going to be bonding with a calcium. So this is not a scenario where there have to be 2 chlorines. So do not, I repeat, do not double that 35.45. That's going to get you the wrong answer. Okay, no Hofbrinkel here. So now we set up factor label problems. We cancel out our grams of calcium since they're on the top and the bottom. We do a division. And when we get our answer, this is different than what I normally tell you, but it's going to be important in this step, since it's not our final step, that we keep 4 or 5 decimal places. All right, and again here when we convert the chlorine from grams to moles, I can cancel out my grams on top and the bottom, and when I get my answer, I want to again keep 4 or 5 decimals. If you don't, that can really throw off the accuracy, the correctness of your answer. Okay, so now we know how many moles of calcium we have and how many moles of chlorine we have. And now we need to start making this kind of look like a formula, you know, where you have symbols with subscripts. So what we're going to do, and this seems weird, is we are going to write out that for calcium we have 0.90094 moles. This is hard to write small here. And for chlorine we have 1.8019 moles. And we're going to write those numbers small like they're subscripts. Okay, and then I'm going to look at those two numbers, the numbers of moles, and ask which is smaller. So obviously in this case, the 0.90094 is smaller than 1.8019. And so no matter what, no matter which side of the formula it's on or anything, I divide both sides by the smaller number. Okay? So I'm going to have to plug those into my calculator, right? But I want to point out now that since I've written and shown you how we got there, what I have here is actually also written down here, right? You have the number of moles of calcium, the number of moles of chlorine, and then we're dividing both by the smallest number. And sure enough, when we do this, we have 0.90094 divided by itself here. That just gives us 1. Right, so we don't really have to write that subscript for calcium. And then when we do 1.8019 divided by 0.90094, we actually get 1.99999, which we can safely round to 2. Which means that this here, CaCl2, is our final answer. That is the simplest formula for this compound. All right, now, I want to do one more problem with you, part of your homework, because the next problem is actually slightly more complex. It has one final step that we have to do at the end that we didn't have to for this calcium and chlorine problem. So let's move down. You may want to do this on a separate sheet of paper because you're going to see I'm going to run into the space where I have space allotted for other problems. So you probably want a separate sheet of paper for this unless you write really small. All right, so remember, we're told the percent of aluminum and the percent of sulfur. We assume a 100-gram sample, which means we can turn those percents right into grams. But a formula is not a gram ratio, it's a mole ratio. So our first step is we need to figure out the number of moles of aluminum that are equal to the 35.94 grams of aluminum. I apologize, it's hard to write small on this. So I'm just going to look up on my periodic table what the molar mass of aluminum is. And it is 26.98 grams of aluminum, right, is equal to 1 mole of aluminum, just like I've been doing since the moles packet. So I cancel out grams of aluminum on top and bottom. I have a little division problem, and I get 1.3321 moles of aluminum. Again, keeping 4 or 5 decimal places. Okay, I'm going to do the same thing for sulfur. So I want to know the number of moles of sulfur that are equal to 64.06 grams of sulfur. So I'm going to look up on the periodic table the molar mass of sulfur, and it is 32.06 grams of sulfur for 1 mole of sulfur. So, factor label, cancel out my grams of sulfur on top and bottom, do a little division problem, and I get 1.9981 moles of sulfur. Again, leaving some decimal places. So now I want to turn this into basically something that's going to start to look like a formula, because that's my goal here, is to write a formula. So I have 1.3321 moles of aluminum. So I'm going to write that as a little subscript. And I have 1.9981 moles of sulfur. So I write that as a subscript. And then I'm going to divide by whichever of those two little subscript numbers is smaller, which in this case is 1.3321. Okay? So for my little division problem here, aluminum, I've got 1.3321 divided by itself, which means I would get Al1. And when I do 1.9981 divided by 1.3321, I get 1.499 something. So I'm going to round that to 1.5. I can't round it all the way down to 1, and I can't round it all the way up to 2 because it's kind of right in the middle between 1 and 2. And if I round that much, it's going to throw off my final answer. My final answer will be wrong. Okay, but at the same time, I cannot finalize my answer right now because I cannot have a decimal in a formula. You've never seen that before, and it's not a coincidence. They're not allowed in formulas. So what I need to do is I need to figure out what could I multiply this whole formula by, meaning both the 1 and the 1.5, that would allow me to change that 1.5 into a whole number. In other words, 1.5 times what would make a whole number. Okay, and this is usually going to be a number like 2 or 3 or 4. These usually don't have to be really big numbers. Okay, so what I want you to think about is the fact that our decimal here that we're trying to get rid of is 0.5. Think of that like 50 cents, right? If you had 50 cents, like a 50-cent piece, I know they're not that common, but let's say you had a 50-cent piece. How many of them would you need to have $1? Well, you'd need to have 2, right? That's your little hint that if you multiply this whole thing by 2, that's going to make a whole number. Okay? So you cannot just multiply sulfur by 2. Whatever you multiply sulfur by, you got to multiply aluminum by. They're stuck together in a compound. So Al has a subscript of 1, right? I do that 1 times 2, and I get Al2. S has a subscript of 1.5. Sure enough, 1.5 times 2 gives me 3. So S3. Now I have a formula that just has whole numbers in it, and so that's my final answer. Okay? The good news is that we're only going to give you decimals that end up being 0.5, so something 0.5, 1.5, 2.5, 3.5, right? In which case multiplying by 2 would always work. Or sometimes we'll give you a decimal that's 0.25. So if you had 1.25, right, think of 0.25 like 25 cents, right, like a quarter. You'd need 4 quarters to make $1. So if your decimal in the formula comes out to be something 0.25, then multiplying by 4 is going to do the trick. Okay, so try multiplying by 2, see if it works. If it doesn't, try 4. If neither of those work, then you did something wrong previously because multiplying by 2 or multiplying by 4 should do the trick for you in these problems. All right, we're not trying to make them incredibly math intensive. All right, also keep in mind that this multiplying step at the end, you don't always have to do. In the first example I showed you, we didn't need to do it. You only have to multiply if what you end up with in your formula is a decimal. Okay, so we will continue practicing the next time we meet in class.